All right, kids, it's time for discussion 3.1, all about chemical bonding. All right, so there's three main types of chemical bonds: ionic bonds, covalent bonds, and metallic bonds. So in this discussion, we're going to talk about each type of these three bonds. We'll talk about the properties of compounds, and we will tell you how you can figure out which bond you have. All right, so first let's talk about the octet rule. So most naturally occurring elements in the universe are not inherently stable. They're not inherently stable because they don't have the correct, if you will, number of valence electrons. Every element will become stable or can become stable if it obtains a full outer shell of 8 valence electrons. This is known as the octet rule. So there's only one set of elements on the periodic table or in the universe that come ready-made with 8 valence electrons, and those are noble gases. So the fact that noble gases have 8 valence electrons explains their chemical inertness and the fact that they do not participate in chemical reactions. They're already as stable as they can be because of that 8 valence electrons. Since all the other elements in the universe don't have 8 valence electrons, they will either lose, gain, or share electrons in order to make that happen and become stable. So let's look at the octet rule concerning metals. So metals react by losing electrons. They lose electrons because they have low ionization energy. That means it's easy for them to lose electrons. They also have low electronegativity, which means they're not particularly too good at gaining electrons. So let's look at an example of sodium. Sodium, because it's in group 1, has 1 valence electrons. So the question is, how many electrons would a sodium atom need to lose in order to have a full outer shell of 8 valence electrons, or to have the same electron configuration as a noble gas? So let's go ahead and diagram a sodium atom. For the nucleus, I'll just write the symbol. Now, sodium has 3 occupied energy levels. We know that because sodium's box in the periodic table resides in period 3. There are 2 electrons in the first energy level. There are 8 in the second energy level, and that 1 valence electron in the third energy level. So if we look at the atom of sodium, if sodium lost that 1 outer electron, since that energy level only contains that single electron, when sodium loses that 1 electron, it will then have an outer energy level, the second, that has 8 electrons in it. So when sodium loses a single electron, it will obtain its full outer shell, its octet, if you will, and it becomes stable. So when sodium undergoes a chemical reaction, because it loses a single electron, it's going to form a charge of +1. And the symbol for the sodium ion would be Na1+. Now let me just explain really quickly how we get that. In a sodium atom, sodium has atomic number 11, so there are 11 protons and 11 electrons. You can count them. 2, 4, 6, 8, 10, 11. So when I add up all of the positive charges from the protons and all of the negative charges from the electrons, 11 protons and 11 electrons, in an atom they add up to 0. But sodium will lose 1 electron when it reacts. So because it's a sodium ion, it still has 11 protons. But when it loses 1 electron, it will have 10. So when I add all of my positive charges to all of my negative charges here, I get an overall charge for the sodium ion of +1. All right, so I want you guys to practice. Now, here's a little tip. For a metal, they're going to react by losing electrons. However many valence electrons they have, that is how many they need to lose in order to have that full outer shell. So first determine how many valence electrons each one has, and that will be the charge on the positive ion. So pause the video and see if you can work these 3 out. All right, so magnesium has 2 valence electrons. That means magnesium has to lose those 2 valence electrons when it reacts. Since it loses 2 electrons, the charge on the magnesium ion will be +2. For potassium, it's in group 1, just like sodium, so it will lose 1 electron when it reacts, giving the potassium ion a charge of +1. For aluminum, aluminum has 3 valence electrons, so it needs to lose all 3 of those electrons when it reacts, forming an ion with a charge of 3+. So the number of electrons lost for an atom, for an element, for a metal, will be equal to its ionic charge. So 2 electrons lost means your charge is +2. 1 electron's lost means your charge is +1, and so forth. Now nonmetals are the opposite of metals, so nonmetals react by gaining electrons. Fluorine, for an example, has 7 valence electrons. So with nonmetals, it's a little bit simpler. To think about, we have to remember that fluorine, like all elements, wants to have 8 valence electrons. An atom of fluorine has 7, so it has to gain 1 electron to have 8. And if it does that, it would have the same electron configuration as neon. So when fluorine undergoes a chemical reaction, because it gains a single electron, it will have a charge of -1. Its ion will have a charge of -1. And the symbol for a fluoride ion is F1-. So for these nonmetals, do the same kind of practice. Now it's a little bit different than it is with metals. In metals, the number of valence electrons a metal has is equal to its ionic charge. For a nonmetal, we have to consider how many valence electrons they have, and thus how many they would need to gain. So pause the video and see if you can work that out. All right, so sulfur is in group 16 of the periodic table. That means it has 6 valence electrons, so it has to gain 2 in order to become stable and have 8. So a sulfide ion has a charge of 2-. For bromine, bromine is in group 17, so it has 7 valence electrons. Just like fluorine, it needs to gain 1 electron, and so its ionic charge would be -1. And for nitrogen, nitrogen is in group 15. That means it has 5 valence electrons. If it wants 8 and it has 5, it has to gain 3, giving its ion charge a charge of 3-. So just like with the nonmetals, or with the metals, the number of electrons lost is equal to the positive charge. For nonmetals, the number of electrons gained is equal to the negative charge. All right, so now that we've talked about ions, let's talk about ionic bonding. An ionic bond, shockingly enough, is a bond between ions. The way it works is an element with a low electronegativity, usually a metal, will come in contact with an element with a high electronegativity, a nonmetal. Because the nonmetal has a high electronegativity, it's really good at pulling electrons off from other atoms. So that nonmetal will pull an electron off from the metal. So we can say that there is a transfer of electrons from one element to the other, from the metal to the nonmetal. Here's an image of that occurring. So sodium here as the atom with its 1 valence electron reacts with chlorine with its 7 valence electrons. Chlorine pulls the electron away from sodium, turning it into a chloride ion, and by losing that electron, sodium becomes a sodium ion. So the metal will turn into a cation, and the nonmetal will turn into an anion. Once you have oppositely charged ions, they will attract each other and stick together. And that is the ionic bond. So let's talk about properties of ionic compounds. They have a crystalline lattice structure. Here's an example of sodium chloride. You can see a clear pattern of alternating chloride ions and sodium ions. Whichever way you look, it always alternates: chloride, sodium, sodium, and so forth. Now, to break the word apart, lattice just refers to a repeating pattern, and crystalline means that in the macroscopic sense, these compounds are crystalline in nature. They're crystals. Ionic compounds have very, very high melting points, and for their conductivity, sometimes they are conductive and sometimes they are not. In the solid form, they are non-conductive. But if you melt an ionic solid or dissolve it in water, make it aqueous, it will conduct electricity. Now, in order to be conductive, the ions in the compound need to be able to move around. In the solid phase, they're all locked in place and cannot move around. But when they're melted or when you dissolve them, the particles, the ions split apart and are able to move around. So when I say aqueous, I just mean dissolved in water. So let's consider sodium chloride. When an ionic compound like sodium chloride is added to water, if it is soluble, it will break apart into the ions that make it up. So solid sodium chloride is mixed with water. When that happens, the sodium and chloride ions that are locked together in the compound separate. And we say that they are aqueous. This state symbol AQ just means dissolved in water. So if sodium chloride were dissolved in water, we could write its formula in a chemical equation as NaCl aqueous. And if a compound is insoluble, then it won't dissolve and it'll just collect on the bottom of the container if you pour it into water. All right, so how do we know an ionic bond forms? There's two ways. One, you can look at the difference in the electronegativity values for each element. So the difference in electronegativity can tell us what type of bond we have. So to find the difference, we always subtract. So you'll be given the electronegativity values for two elements, subtract one from the other. If the difference is greater than or equal to 1.8, then the bond is ionic. If it's less than 1.8, it would be a covalent bond. So we know that sodium and chlorine will form an ionic bond. This was the example we used earlier. So sodium has an electronegativity value of 0.9. Chlorine has an electronegativity value of 3.2. If I get the difference between those electronegativity values and it's greater than 1.8, that tells me the bond is ionic. And indeed, 2.3 is greater than 1.8. The other way you can tell is just look at the elements on the periodic table. If it's a bond between a metal and a nonmetal, then it will be ionic every single time, at least for all intents and purposes. So two ways, electronegativity difference, or just looking, metal and nonmetal means ionic. All right, now let's talk about covalent bonding. A covalent bond is a bond where electrons are shared between atoms, as opposed to the transfer that we see in the ionic bond. In a covalent bond, each atom will supply one of the bonding electrons. So here I have drawn the Lewis structures for oxygen, hydrogen, and nitrogen. So oxygen has 6 valence electrons, hydrogen has 1, and nitrogen has 5. When a bond forms between these elements, the lone electron in hydrogen will be shared with oxygen to make bonds between hydrogen and oxygen. So we can see in this example here, oxygen's electrons are these little orange circles and hydrogen's are the blue circles. The bond between hydrogen and oxygen consists of 1 electron from oxygen and 1 from hydrogen. Each atom supplies an electron to make the bond between them happen. If we look at nitrogen versus hydrogen, nitrogen has 5 valence electrons, so nitrogen's electrons here are this bright orange. Each bond between hydrogen and nitrogen involves 1 electron from hydrogen and another electron from nitrogen. Each atom is sharing these electrons. Now, if we look for oxygen, once hydrogen shares those 2 electrons, oxygen is surrounded by 8 electrons. For hydrogen, remember, hydrogen only has 1 electron, so its full shell, the first energy level, is full when it only has 2 electrons. And we'll talk about the shapes of molecules in topic 3 of this unit. All right, so compounds with covalent bonds are called molecular compounds. They're not called covalent compounds. They're compounds that have covalent bonds. But they're called molecular compounds because these compounds exist as individual molecules, whereas in an ionic compound, it's just a never-ending crystalline lattice. So you can recognize a covalently bonded compound because the atoms in the molecule will all be non-metals. All right, so let's just talk quickly about some properties of molecular compounds, and you'll see how they contrast to ionic compounds. So ionic compounds are always solid, every single time. Molecular compounds are generally liquids or gases. Ionic compounds have extremely high melting points. Molecular compounds generally have low melting points. That's why they're liquids or gases. Most, I can't say, we never like to say all or never in chemistry. Most molecular compounds are non-conductive. All ionic compounds will conduct electricity when molten or dissolved. Finally, I want to talk about metallic bonding. So in a metal, like copper or aluminum or sodium or any other metal, the valence electrons in the metal atoms detach. And so what we end up getting is a lattice of cations. The thing that holds the metal together is the attraction between those metallic ions and the valence electrons, which move around. So here's a diagram of that. It's just a lattice or a repeating pattern of cations with electrons randomly sprinkled throughout. Now these electrons are what are known as delocalized, which means they're free to move around. Sometimes you'll see this referred to as a sea of electrons. So this sea of electrons explains why metals are good conductors of electricity. Electricity is just electrons moving. So these electrons are able to be moved around the structure, so metals are good conductors. Also, the bond between these cations are not rigid bonds. If we go back and look at the bonds between hydrogen and oxygen or hydrogen and nitrogen in this covalent or molecular compound, these are rigid bonds. These hydrogen atoms can't move around in relation to one another. Think about it like being a stick holding the two atoms together. In a metal, we don't have that rigid bond. So if I smash this corner or a corner of this metal with a hammer, no bonds actually get broken. But because there are no rigid bonds between these, it means these atoms can move in relation to one another. So that nature of metallic bonding explains why metals are malleable and ductile. When we smash it with a hammer, instead of breaking apart, it just will dent. And that is it for discussion 3.1. Again, this is a very, very, very important discussion. So make sure you master, especially determining what the charge on an ion is. And thanks so much for watching. Have a great day, everybody. Thank you.